Okay, so these two identities you will require to solve some of the problems in the tube. I think the voice is better with this. Not here, but on the videos. Okay, so now what we've seen was, till now we've seen the first law, and merely we can, what we've seen is du is equal to dq plus dw, right? And that the cyclic integral of du is equal to 0, right? First? Sure. We can go back here, no problem. Yeah, I have told people in the tubes, but I think everybody's not had a tube. Who's Neha? You did not inform these two people? Yesterday they were standing outside my office. So, we'll have it today. The Friday batch tube after the class. Whoever wants to attend, it's fine. It's fine? Okay. Right. Now the things are not very many over here. The thing is that the first law says that there is conservation of energy, very true. There's no doubts about it. But when we want to really make use of it, so I would imagine, okay, I do some work, the system does some work. Yeah? Everything fine? So the system does some work, and you need to pump heat into the system. Right? And the amount of heat that you pump into the system can be converted to work. That's what the first law says. Yes? But in reality, this is not the truth. And that's where the second law comes in, which says that if I put heat into a cycle and I want to get work out of that, it's necessary that I must waste some heat. Okay. So, yeah, sit down. So the way I could depict is that, let's say we have a hot reservoir from where I can take out heat, which is at temperature T1, it's hot. And this is my system, which is doing some sort of a cyclic work. Okay, let's make it a bit bigger so I have place to write. Okay, and then I want to extract work out of it. Okay, so I put some heat Q into this cyclic system. I do some cycling. I want to get work out. This is not possible. Okay, what is possible is that I must dump some heat. So let's say this is Q1, this is Q2, into a colder place. Heat can only flow from a hotter place to a colder place. That's the second way of looking at the second law. This one says, if you want to get some work out of a system, you must lose some heat. Okay. So the picture is not so rosy. No gain, no pain scenario doesn't hold true. You do have to lose some. This doesn't violate the first law. Okay, be very careful. So whatever heat is coming in goes either as work or as this heat lost. There is no violation. Only it says for practical purposes, you cannot have a no gain, no pain, no loss situation. Good. The other way of looking at this fellow is that Okay, maybe I can even put some signs over here. Since I am talking of work done by the system, that would be a negative sign over there, right? The work done would be negative. If you understand that, then I can leave the signs. Okay, then I'll just leave the signs, no problem. Yeah, so the work done is negative, this heat loss is negative, the heat put into this, so this is our system, this cycle is our system, right? So the heat put into the system is positive. Right? So that's one way. The other way of looking at the same thing is in a sense of a refrigerator, that we want to extract heat out of a system. Right? So if I am extracting heat out of a system to make it cold, I have to throw this heat to a hotter place. Now, the alternative statement, right? I have to throw it to a hotter place. That's what an AC does, that's what a refrigerator does. It's cold inside the refrigerator, hot outside. So I'm taking the heat out of the refrigerator, throwing it to the surroundings. Right? So if I have to do that, that must involve some work. So if I have to remove heat from a cold reservoir and pump it into a hot reservoir, I must do work on the system. That's another way of looking at the second law. So this is T1 hot. Again, the cycle of changes, and T2 cold. Right. So now heat flows from the cold into the system. Yes. So Q2 would be positive. Heat flows from the system to the surroundings. Q1 should be negative. Work goes into the system. Work should be positive. Right? That's right. It's better I put the signs over there so that you don't ask me again and again. Negative, negative, this is positive, that's negative, that's positive. Right. So, yes? See, I'm taking heat out from the surroundings. I'm throwing out heat into a colder surrounding. Yes. I'm doing some work. So this is positive, this is positive. This is all entering the system. This is the one that's exiting. Which means necessarily that whatever heat I'm throwing out into the surroundings is less. If I take the absolute values, forget about the signs, it's if you take the true value, then also it's less. It's anyway negative. You take the absolute value, so I'll be able to throw less amount of heat from the colder system to the. So I absorb some heat from the cold. I throw more heat into the hot. That is the reason why you cannot open a refrigerator door in your room and expect the room to heat up. Sorry. Sorry?
Why is there a need for the heat to be
Why? That's practical knowledge. That's the second law. That's what, see, a law, I cannot prove a law. Right? Can you prove a law? No. First, can you prove a law? Can you prove the gravitational law? Or the Coulomb law? So that's all. When people did experiments, they knew that no matter what you do, You just cannot take out heat without doing some work on the system. All the laws of nature are from experience. They are not provable. In maths also, there are axioms, there are laws, they are there, yes. Some of them are intuitive, some are not. This one is quite intuitive for that matter. Yes. No. It's not intuitive. Huh? It's not, this one is not intuitive. It's not. For some it's intuitive, okay, some people say it's not intuitive, but I don't know. I've never seen any 100% efficient systems. Yes? This is only talking of efficiency. If I can convert, if I can just remove heat from the system without doing any work, then I don't have to worry about my electricity bills. Yes? If I could put in heat into the system and get some work out, all my internal combustion engines which are less than 30% efficient, all our car mileages would, kitna deti? That question won't come. I'm sure everybody's seen that ad. Yeah, so that's the concept of a engine. If I can write. And that's more of a refrigerator. Yeah, so this is just from experience that you put a law. Okay. And the laws of thermodynamics till now have not been broken. In fact, even today, people try a lot to, show that the second law can fail. And every year you will find papers saying that we have invented a perfect engine. That things are going in the opposite direction of entropy. Entropy defines the direction of time. So things are going in the opposite direction. But each and every paper that comes out has a problem. And the problem is mostly over here. To define the system. That's very important. There's a system, there's a surrounding. Right? If you don't calculate for both of them, you can land your system problem. There are a lot of things that happen which lead you to think that the entropy is decreasing. Right? And I'll show you some examples also. But in that case, well, of course, a tree grows, we grow. It seems as if the entropy is decreasing. Some more ordered form is coming into shape. Right? But we've not considered the entropy of the surroundings. I'll show you some very small examples which will prove crystallization, for example. Yeah. Things crystallize. They come into more ordered structures. That means the entropy of that particular thing, that particular material, is decreasing. Very true. But the total entropy of the universe increases. That's the second law. So, when something crystallizes, there's a lot of other things around. For example, the solvent, which was actually attached to these molecules, is now freed up. Right? So you have more degrees of motion for these solvent molecules. We'll calculate some of these things. Don't worry. So yeah, but the main thing that the laws are based on experience. Nothing more than them. We can't prove them.
Then we can explain them.
That much I can do.
Yeah, like you could just say that the law is correct. Doing something like probabilities or mathematics, you could think something.
So we cannot prove them, one thing, Okay, we can only disprove laws. Okay, so we have to find a situation which does not fit this law. Okay, as of now, there is no such situation which does not fit the laws of thermodynamics. Okay, there were situations which did not fit Newtonian mechanics, and that's why quantum mechanics came in, relativistic mechanics came in on the two sides of the spectrum, right? Till then, Newton's laws are just laws. You can't prove them. Can you? No. You do experiments and then you say, okay, this fits the data, so the law is valid. And then one day, you try to apply the law on atoms, it doesn't work. Right? And then you come up with a new theory, with a new law, the Schrodinger's equation, which you'll learn in the second half of this course. Right? That's the way it works. So this is the starting point, this is the basic point. Okay. And Schrodinger's equation is not intuitive because you've not seen atoms. Right? This is from common everyday experience. This is more intuitive. There you'll be able to figure out something, yes, but it's not very intuitive over there. Okay, so coming back to this, now we say that okay, we need to if you are running an engine and we need to get work out of the engine. Just a moment. So if we need to get work out of the engine, we must lose some heat. If we need to extract heat out, in case of the refrigerator, we must do some work. Okay? Fair enough. Let me read out some statements. The first one is for the engine. This is the Kelvin statement. It is impossible for any system to operate in a cycle. In a cycle is very important. Okay? When you see these people who are reporting the collapse of the second law, more often than not, they're not working in a cycle. That's very important. In a cycle that takes heat from a hot reservoir, and converts it to work in the surroundings. You're doing some work on the surroundings without at the same time transferring some heat to a colder reservoir. It is impossible. Huh? You want me to repeat this statement? Well, it's exactly a more formal way of saying what I've said. It's impossible for any system to operate in a cycle that takes heat from a hot reservoir and converts it to work in the surroundings without at the same time transferring some heat to a colder reservoir. These are things you can find on the net also. Kelvin, if you write Kelvin's statement, you'll get it. The other one is by Clausius. And Clausius' statement is more for the refrigerator. It says it is impossible for any system to operate in a cycle. Again, it's very important to operate in a cycle that takes heat from a cold reservoir and transfers it to a hot reservoir without at the same time converting some work into heat. Okay. This is common sense. Heat flows from a hot place to a cold place. It doesn't flow from a cold place to a hot place. Now is it more intuitive? Huh? Okay. So there are some alternative statements which I could just write. Again, this is due to Clausius. This is the one which is more closer to the maths that we'll be using. So it says all spontaneous processes are irreversible. All spontaneous processes. It's very important to understand what's spontaneous. Spontaneous is something that happens by itself. Okay. A ball sitting on the top of the hill would come down, or rather on the slope of the hill would come down. The top might be a flat. That's a spontaneous thing. A ball sitting on the top of the hill should definitely come down. And it's spontaneous, right? If it was on the slope, it would immediately come down. That's also spontaneous because it would lose energy. This is also spontaneous. If it's sitting on a flat top, it has to come down. It's spontaneous, right? But it will not come down because it's not instantaneous, right? What it says is that the energy is lower, so it has to come down. But then there is something that is stopping it. It's not in motion. It's sitting over there. Unless I provide that push, it will not come down. Right? Although it's spontaneous. It's a spontaneous process because the energy is being lowered. Right? But it will only come down if I give that push. An example for chemical reactions would be if I mix nitrogen and oxygen gas. Okay. It's spontaneous that they should form water. But it is really very, very slow. It does not form. It's not instantaneous. Because later on in the kinetics course, you'll see that there's an activation energy barrier which it has to cross. Like a ball, it has to cross this activation. It's just very slow in this case, but it has to be pushed. Same way, the hydrogen and oxygen also have to be pushed. Okay, now apart from this, there is the mathematical statement which will derive, or kind of derive rather. Because again, it's a law, yeah? Which says that d, not two d's, dq by t, okay, is greater than equal to 0. It's a very famous inequality, the Clausius inequality. Right? We'll see how it comes about. You've already seen some of these cycles, right? And you've already realized that dq reversible by t. Remember, you've already seen in some of these cycles that integral, the cyclic integral dq reversible by t is actually equal to 0. There I have not used reversible or irreversible. This is yeah. Right. This is dq reversible by t. No, sorry, what did you ask me? We'll come to that. And you will see how it matters. Okay. For the moment, it's just dq by t. dq reversible by t is 0. What it means is essentially that integral of dq irreversible by t is no, I think I've made some mistake. I already knew I had made some mistake. Please, very sorry for this. Yeah, Clausius would be groaning. Huh? He would be turning in his grave now. So, what it says is dq irreversible by t, then definitely should be less than 0. Don't worry, we'll derive it. Okay.
This is written for a system or universal? For a system, it is written dq.
It's for the universe, but we'll come to it. Don't worry. Okay. This is the total change. We'll come to it. Okay. Now, the thing is, we need to see how this comes about, and we need to link the mathematics with the physical observations. And we do that by using the Carnot cycle. I'm sure some of you have heard about the Carnot cycle. So, now what you do in a Carnot cycle is do some reversible changes. Okay. So, let's see on the pressure volume diagram what these changes look like. Right, I start from one point over here, okay, and I do an isothermal expansion. So I come to another point. So this is isothermal, let's say temperature T1. Then I do an adiabatic expansion. Adiabatic. We come to temperature T2. Then we go back. So this is again an expansion, right? The gas is expanded adiabatically. So the temperature T2 is less than temperature T1. And then I compress it back. I want to make a cycle. I compress it back isothermally. So that's an isothermal compression. And the last step in the cycle would be to compress it adiabatically. So you could label them 0.1, 0.2, 0.3, 0.4, something like that. Right. So I have done some work in the cycle. Yes. I have expanded the gas first isothermally, then adiabatically, compressed it back isothermally, and compressed it back adiabatically. Right. And now I wish to calculate what exactly is the efficiency of this cycle. Right. So the efficiency would be defined as the work done by this engine divided by the heat that has been input into the engine. Right. So let's consider all the 4 parts of this cycle and see what is the work done in each case. Right. So path 1 to 2, that's isothermal expansion at temperature T1, right? So delta U is simply, let's say, Q1 plus W1. Okay. The second one, so let me just write somewhere path 1 to 2. Then path 2 to 3, it's an adiabatic path, right? So Q is 0. The work done would be, let's say, W1 adiabatic. 3 to 4 is again an isothermal compression, right? So that's Q2 plus W2, and 4 back to 1, it's again an adiabatic compression, right? Q is 0, this is just W2 adiabatic. Now see, wherever there are these subscripts 1, that means work is done by the system and heat gets into the system. Wherever we have subscript 2, work is done on the system, right? And heat goes out of the system. So that's just makes it simple. Now if I want to see the efficiency, that is the total work done, which would be the sum of all the works done by the system on the system. So I just need to add up all these works. So efficiency, which we could define as epsilon, is equal to the total work done by the total heat that is input, right, which is equal to W1 plus W1 adiabatic plus W2 plus W2 adiabatic divided by, what is the heat input into the system? Just Q1. Q2 goes out of the system, right? Q2 is just a heat loss, right? Now, how do we go about? Yeah, to our rescue, we have the first law, which says that in a cycle, delta U should be 0. Very good. So cyclic integral of du is equal to 0, and I have already calculated the delta U's for all the 4 paths, right? So what I have is essentially W1 plus W1 adiabatic plus W2 plus W2 adiabatic is equal to minus of Q1 plus Q2, right? So straight away I could just write that the efficiency epsilon is equal to minus of Q1 plus Q2 by Q1, or if I don't want the minus sign with the efficiency, then what I can do is to put a minus sign over here, because that's more correct. What I want is the work that has been done by the system, right? So if the system does some work, then this total should be a negative quantity, right? If the system does some work on the surroundings, then this is the total work done. This should be a negative quantity. So to make it positive, I could put a negative sign over there, and then that's the efficiency. So the signs are inside, right? We are following one sign convention. Work out, work done by the system, negative, work done on the system, positive. Heat into the system, positive. Heat into the system, heat into the system, positive. Heat out of the system, negative. So this Q2 would be a negative quantity. Q1 would be a positive quantity, right? And because of that, if I just write this equation like 1 plus Q2 by Q1 Yeah, the efficiency, since Q2 is a negative quantity, the efficiency would always be less than 1 or less than 100%. Right? And the second law clearly says that Q2 can't be 0. You have to lose some heat in the engine. Right? So Q2 can't be 0. So it's always, this quantity is always less than 100%. Right? So whatever the work that has been output to the system, the work minus W that has been output to the system, which is the sum of all the works, is simply equal to the heat input into the system times the efficiency. Right. So these are some things which, okay. Let's go ahead one step and let's see the Carnot cycle for an ideal gas. Let's calculate some quantities for an ideal gas. Okay. So delta U in the first case, let's go back, or maybe I can draw it again quickly. Isothermal adiabat, isothermal adiabat. So T1, T2, adiabat, adiabat, 1, 2, 3, 4. Okay, pressure, volume. Fine. So path 1 to 2, delta U is 0. It's isothermal. Now, so let me just write. This is, remember, this Carnot cycle that we drew, these are all reversible changes. So let me just remind this is all reversible. And we are doing again for a reversible case, ideal gas. So what does this give me? This gives me quickly Q1 is equal to minus of W1 and W1 we already know is RT1 log of sorry, V2 minus V2 by V1. So that's 1 to 2, then 2 to 3. Q is 0, right? It's an adiabat. What's W1 adiabatic? CV delta T, right? T2 minus T1, right? And since it's a reversible adiabatic case, I have another equation from there. T2 over T1 is equal to V2 over, so volume at point 2 over volume at point 3, right? This could get a bit confusing because T2 is the temperature over here, sorry, T1 is the temperature here, T2 is the temperature here, but the volume is V2 and the volume is V3. To the power gamma minus 1. Right? The notation could get a bit confusing, so please be careful. Now, again, in the step 3 to 4, we again have delta U is equal to 0, right? And Q2 is equal to minus of W2, right? Which comes out to be R T log V4 by V3, right? Yes? Great. And step 4 to 1. Q is 0 again. W2 adiabatic is what I want. Maybe I just use some other color so it becomes easier. 4 to 1. Q is 0. W2 adiabatic is equal to CV T1 minus T2. And over here again I have this equation T1 by T2 is equal to V4 by V1. V4 by V1 per gamma. That's correct? Yeah. So I have all these equations over here. Do some substitution. I know what is Q2, I know what is Q1, I know the total work. Let's calculate the efficiency. Okay, let's do this exercise and get Q2 by Q1 is equal to minus of T2 by T1. See, the efficiency is 1 plus Q2 by Q1.
So that should be R T2.
Which one? Ah, thanks. It's not just T. You're right, T2. Up there, it's T1. That's fine. Okay, so do this exercise quickly. Let's write the total work in the numerator, total heat in the denominator, and we get this relationship. I have not yet come to entropy. I am deriving entropy from here. Right? You're right, otherwise. What I have to come to is to show you the Clausius inequality first. Got it? Okay, so as she said, conservation of entropy would show this, but I was actually doing the other way around. I was trying to show the conservation of entropy from here to tell you that if I put Q2 by T2 plus Q1 by T1, then it's 0, or in other words, dq reversible by T is equal to 0. That's what I was trying to show you from here. Okay. Yeah, once we know this, we can always do the other way around. And once we have this, then my efficiency just comes out to be 1 plus Q2 by Q1, right? Which I can also state as 1 minus T2 by T1. Question: when can you have 100% efficiency? T2 equals 0. Oh, that's the third law. Huh? That's the third law. This is possible. No, that's the third law. But the second second law also says that if you want 100% efficiency, you have to go to 0 Kelvin. Or maybe T1 could be infinite. Either ways. Right. Okay. So only if T2 approaches 0 Kelvin. Yeah, we don't write the degree when we write Kelvin. So it approaches 0 degree, you can say degree Kelvin, but you don't write it. Then the efficiency 100%, otherwise not. Okay. Now what more do we want to prove over here? You have something else?
Why can't T2 approach 0 Kelvin?
No, it can approach 0 Kelvin. Who said it can't approach 0 Kelvin? It can't go to 0. It can't go to 0 Kelvin. That's the third law. We'll come to it.
T1 is higher than T2. If T2 approaches to 0, then T1.
It will approach 100%, but won't be 100%, right? Okay. If you want to really see that why it cannot approach 0 Kelvin, let's go back. Let's go back to the refrigerator. What's the work done in case of the refrigerator? Huh? Q2 minus Q1, which if I want to express in terms of temperatures, I could write Q2 minus Q1 divided by Q1 multiplied by Q1. That means I can write T2 minus T1 divided by T1 multiplied by Q1. Right? So what is the work done in that case? Huh? If I want to go to 0 Kelvin, what is the heat that is input into the system? In the refrigerator, Q2, right? And I've been talking in terms of Q1. So let me just write it down. Huh? What I'm saying is that the work done is equal to T2 minus T1 over T1 times Q1, right? But Q1 is not the heat input. I want to see how much is the work done compared to the heat input. So let's change it to Q2. We already know Q2 by T2 is equal to minus of Q1 by T1, right? So what does it come out to be? Minus T2 plus T1 by T2 into Q2, right? So this is the amount of work that needs to be done if I wish to have 0 Kelvin, right? So this is right. T2 is the cold part, yes, and I want to bring it down to 0 Kelvin. Remember the refrigerator, I am bringing out Q2 heat out of the refrigerator, and the temperature of the cold reservoir is T2, and I am throwing Q1 heat into T1, which is at a higher temperature, by doing some work. So if I want to bring the temperature of this cold reservoir down to 0, then I have to do infinite amount of work, right? Yes. good. Why everybody is so confused in that case? Okay, was it too simple, too obvious? No, I hope not. It's fine. That's actually the third law, that you have to do infinite amount of work to achieve 0 Kelvin, and that's why you cannot achieve 0 Kelvin. Okay, let me tell you one very profound fact, and that is you cannot have a reversible engine which has an efficiency other than the reversible Carnot engine. Okay, if there is a reversible engine, its efficiency has to be the same as that of the reversible Carnot. Agreed? Very fast. Nobody wants to prove it? Prove it, okay. Let's not prove it mathematically, let's just do a hand waving argument. Let's say we have a Carnot engine and its efficiency is epsilon prime. At least let's write this thing down. Epsilon prime, and this epsilon prime is greater than the efficiency of the engine that we are looking at. Both are reversible. Okay. Now, we could use, since the efficiency of the Carnot engine is high, we could use this particular engine as an engine and the other one as a refrigerator. Okay. So since the efficiency of the Carnot engine is high, it will be doing some work. Okay. And since it's higher than it, epsilon prime is that of the Carnot. That's any reversible engine. Carnot is also reversible. Okay. So since this is an engine and it's doing some work, right? That work, I can use that work to do work for the refrigerator, right? And since the efficiency of the refrigerator is lower, it would actually take out heat from, it will need less amount of work, it will take out heat from the cold reservoir and pump it into a hot reservoir. Right? So essentially, I really don't need to do any work. I'd be pumping heat from a cold reservoir to a hot reservoir without actually doing any work. So we have this two engines over here. Let's just draw that also. So we have this T1 hot, and we have one of these engines, T2 cold. Okay. Now the first one, let's say that's my Carnot engine, and this fellow is taking up some heat, Q1. Okay. And it's doing some work, W, and this fellow is giving losing some heat also. Now I have another engine which actually needed some work, W prime, I guess. So in this case the work is going out, okay. In this case the work is going in. I'm using this as a refrigerator, right? Okay. So, I spoke everything right. The only thing is I have written, what I have written is Carnot efficiency is greater than the other one, but I have put the primes on the other one. So let me just change that. Let's make the
Carnot and reversible.
huh? Huh? I could have done that. Only thing is in my notes it's the other way around, and then I would have confused myself more and you also. Okay. Right. So now what I can do is, since the efficiency of this Carnot fellow is more, okay, so I can actually remove some work out of this and use this work to pump heat from the cold reservoir to the hot reservoir through the reversible engine. Yes? I need some work for this reversible engine, right? And that work can come from there. Which means that I don't have to do any additional work. I can pump heat from a cold reservoir to a hot reservoir. No?
So if reversible is just so
Ah.
you need more work.
So let's, in that case, show you more mathematically.
So the reservoir at some point of time changes temperature.
These reservoirs are assumed to be large ones.
No, if they are living conditions, then T2 will become more and more less, and T1 increases.
If you have a small reservoir. The thing is that when you talk of reservoir, you think that this is a constant temperature.
Okay, any comment about the magnitudes of Q1 prime and Q1? Please comment about that.
Yeah.
What is greater only?
Let's do that. So what is essentially what is required? I said that efficiency epsilon is greater than epsilon prime is greater than epsilon. The efficiency of the Carnot engine. Now, which means that the work done by the Carnot engine is more. So the work output by the Carnot engine, W prime, divided by the heat input into the Carnot engine, Q1 prime, is greater than minus W by Q1. Right? If that is the case, then this just means that W, I just changed some signs. No. I'm talking of engines. Right? I'm talking of the efficiency of the engines for the moment. Okay. Of the engines.
But that is
I'll just come to it, don't worry. Right. So we have again W prime by Q1 prime is greater than, so minus of that, minus of W by Q1. But what's the total amount of work done? The total amount of work done is total work output from this engine is actually 0. Whatever work is being done by the Carnot engine is being taken up by the other one. Right? W exactly. So whatever that W prime is the work being given out is equal to W. These are connections. I take it to engine and connect it to what is the amount of work that is being delivered to the surroundings? How much amount of work is being delivered to the surroundings? Zero. Whatever Carnot engine is, whatever work is being given out by the Carnot engine is being taken up by the reversible engine. Right?
Sir, sir, if you consider that the Carnot, engine and the other separate systems.
Yes.
Then applying the second law means some each of the laws we transfer some work from one first reservoir to the second one. How can we W prime equal to the?
See, what I'm saying is that I've coupled the two engines together. Okay. The first thing is that I've assumed that the two efficiencies are different. Okay. Now I have two engines. Right? Reversible engine. Huh? So all these reversible engines, they can function as refrigerators. Right? So what I've done is, since the Carnot engine is more efficient, it is giving me more work compared to the other one. Right? For the same amount of heat that comes in. Yes? So what I've done is, I've taken this work and I'm pushing this work into the reversible engine. Okay? So now when work goes into this reversible engine, it starts to behave like a refrigerator. Yes? That's all the case is. Huh? What is the efficiency? Efficiency is the work that has been output divided by the heat that is input. Right? That's the efficiency. Okay. What is the input divided by, sorry, what is the output that is divided by the input?
Yes, sir. So what is the output that is given to the thing? That is rejected.
No. The engine is doing work, right? Engine is meant to do work. Mechanical, whatever work. So the output work divided by the input heat. That's all. So that is. Sorry? No. See, what is the efficiency of this engine? See, these are two engines. These are all reversible. The efficiencies are the work produced by the engine divided by the heat inputted to the engine. Right? Okay. Now, if I am going to connect the two engines, right? These are nothing but there are some things which can act reversibly. Yes? Now if I connect the two things together, the first one is the Carnot one is more efficient. So it will give the work to the reversible engine. Right? If work is being pumped into the reversible engine, then it acts like a fridge. Right? Then what the fridge will do is, because it's taking in work, it will extract some heat from the colder reservoir and throw it into the hotter reservoir. No. See, what I'm saying is the efficiency of the engine, not of the fridge. I'm worried about the efficiency of the engine, because this is the engine that is going to work. Yes? If I don't worry about the efficiency of the engine, then I cannot say that this work is going to drive this as a fridge. Okay?
That is because by default we choosing to take heat from the hot reservoir.
Right. That is what the efficiency is defined. The efficiency of an engine is defined as the work done, work output divided by the heat input. The other one, okay, what we are talking of is the coefficient of refrigeration. I have not talked about that till now.
Sir, what is that minus W by Q1?
Huh?
Minus W by Q1.
So this is the efficiency of the Carnot engine.
Yes, sir.
This is the efficiency of the
On the
reversible engine. Q1 or Q1 prime? Yeah, Q1 prime is there, right?
Sir, in that minus W by Q1,
Right.
second minus W by Q1, sir, it is the efficiency of Q1, right? So, the minus W by Q1, sir.
Yes, sir.
Yes, sir. This is the efficiency of this.
The reversible engine. See, that's what I'm denoting by the primes the Carnot engine, and without the primes I'm denoting the reversible engine. Right? What I'm trying to prove, what I said was that any reversible engine would have an efficiency equal to that of a Carnot engine.
So we take the cycle with the 2 isobars and 2 isopoles and calculate its efficiency. It's not coming.
If it's a reversible one, it will come out to be the same. Okay? And that's what I'm just trying to prove. I just said, in a hand waving argument, I just told you that if you drive these engines, what it means is that you will extract heat from the cold reservoir and throw it into the hot reservoir. Yeah? And since the gentleman out here wants some more details, right? So the work done by the Carnot engine is the work input for the reversible engine, right? So what I can write then is, instead of minus W prime, I can just write W. So W by Q1 prime is greater than minus W by Q1. Yes? If I can write it that way. And I know that Q1 is less than minus of Q1 prime. Since Q1 is a negative quantity, yes, I am throwing heat from the system to the surrounding, and Q1 prime is a positive quantity because heat is coming from the hot reservoir into the system in case of the Carnot cycle, in case of the Carnot engine, right? So since this is the case, all it means is that Q1 prime plus Q1 is greater than 0. So I'll just write it down, no problem. Q1 is for the reversible case, which is now acting as a refrigerator. So which means heat is going from the system to the surroundings. So Q1 is less than 0. Q1 prime is for the Carnot engine, which means heat is coming into the engine. So Q1 prime is greater than 0. Sorry. Otherwise, I would have proved the opposite thing. So, Q1 prime plus Q1, which means is less than 0, which violates the second law, right? It just says that we are removing heat from the cold reservoir and pumping it into the hot reservoir without having to do any work, right? Yeah, now. So all it means is, if there is any difference in the efficiencies of the two cycles which are reversible, that is not possible. So whatever is the efficiency of the Carnot cycle would be the efficiency of the other reversible cycles. So you could actually try out some of this. Yeah. Yes. Reversible. Yeah, so maximum means reversible, right? If it's irreversible, it will come. No, it can't. That's what I just proved. It has to be equal. If it's greater, then put it the other way around and we'll recover the same thing. Yeah?
Please give us an example of such cycle, reversible cycle, how it will be between the temperatures, even T2 that can be any temperature, temperature.
Any two temperatures, right? See the efficiency.
Then consider two Carnot cycles.
Yes.
Working between two different temperatures. This is even T2 and this is even at T2 dash.
The efficiency depends on the working temperature, right? Efficiency is 1 minus T2 by T1. Okay. So if you can choose such temperatures such that the efficiency is same, that's okay. Q1 is less than 0. So Q1 is less than 0 and oh, the minus should be there. No, it's fine, it's fine, it's fine. It's okay. So I cancel W and the minus sign stays. I take Q1 on the other side and Q1 prime on the other side. So thanks. एक मिनट यार, क्यों मुझे कंफ्यूज कर रहे हो? I take Q1 on this side in the negative sign, right? So it will be minus of Q1 prime is less than, fine. ठीक है ना? अरे वो अभी भी कहते हैं ठीक नहीं। क्या कर रहे हो तुम जो गड़बड़ कर रहे हो? मुझे भी कंफ्यूज कर Q1 is negative.
Everywhere carrying negative sign with Q1, that negative sign, extra negative sign. So that minus Q1 small becomes positive. And then we take it from that side.
It's there, the signs are inbuilt. I don't have to worry about the signs. This statement, what does it say? What does this, okay, just a moment. What does this statement say? Yeah, that means my hotter source is getting colder. Sorry, the hotter source is getting hotter and colder is getting colder. Hmm.
So it would have a negative sign. Okay, and Q1 is the heat going in, so it would have the positive sign.
Yes.
And if we add a negative and positive quantity, here it is giving negative sign. So again, total heat is coming out.
Total heat is going in. Look at this.
From that, sir.
But look at these values.
Again, the sign is wrong. Yes, sir.
Array, the sign is fine. Please don't confuse yourself.
Okay, and sir, another stuff. Sir, we haven't used anything for the reversible engine. Any fact that the engines are reversible. Such that
That's why. It's reversible, and that's why the engine can act as a refrigerator. But their efficiencies would not be the same, right? Okay. So enough confusion with this. Great. But I think it's sorted out.
लास्ट में क्या बताया सर समझ में नहीं आया
Huh?
लास्ट
So if u1 dash plus q1